Hello everyone. Hopefully we can clear up some of the problems with our ambiguous case in the law of sines. And so it's all about recognizing the situation. And the first thing we got to do to recognize it is look for two sides in a non-included angle. Now, you're not guaranteed to have the ambiguous case here, which makes this this is why it's tough to recognize it, because you're not guaranteed to have it. And so what I'm going to do is talk you through the four possible things that could happen when you're given the side-side angle condition for solving triangles. And anytime I deal with this, I'm going to be consistent in how I set up my diagram. And I think we really need to emphasize the importance of our diagrams. And so what I always do is start off with the unknown side of this triangle, because you're given two of them. And so I started on the left, draw to the right, arrow represents we don't know how long it's going to be. And so then from here I go and start with my angle. And so for the example that we're going to use in our problems, we're going to start with, let's see, 25 degrees. Now, 25 degree angle. Now we're going to go to the next part that we know, which would be a side. Let's go with 12 in our examples. And the problems with the side-side angle case start coming in when you take the third part, the second side of the situation. Because how do you know exactly where to draw it, where that third side is going to intersect this, or where that second side is going to intersect this infinitely long third side? And so best way to deal with that is the compass. Center point at the vertex and radius set to the side length that you want. And so when you swing your circle, wherever that circle hits this third side is the third vertex of your triangle. Alright, and so whatever that side length is not only the side length of the triangle, but the radius of our circle. And so what I'm going to do as I go through the four cases is you're going to see a red circle in behind my triangle, which represents the circle that I'm swinging to find where that third side and second side intersect. That is, back in geometry, we referred to this as the big side, small side angle condition. And that's where the bigger of the two given sides is opposite the given angle. And so for our example here, we'll just say this side is going to be 14. And so when you go and start drawing your circle and sweeping your circle through, you find that you only hit this infinitely long side in one place. And so we have one triangle that meets this condition, which is why we said the big side, small side angle was a triangle congruence theorem back in the geometry days. And at this point we can use our law of sines. Remember, this side right here is also the radius of the circle. And so now we can go and use our law of sines to first, let's call this angle A over here. I would go and find angle A first. 14 over the sine of 25 degrees equals 12 over the sine of angle A, and then go through and solve. And I think we're good at the triangles. When we have a triangle we can solve. This is more about recognizing the ambiguous case. So let's look at the next situation that occurs. The next situation that I want to look at is the possibility where no triangle is formed because this side, the second side in the series here, is too small to hit this infinitely long side. And so in this particular case, no triangle is going to be formed. Now in terms of us doing our problem solving, we probably won't recognize this situation until we start going in and solving the triangle. So I could see this situation happening right here, because how do you know if that triangle is going to be formed or not? And so we might have 12, 4, 25 degrees. And let's go and find angle A here. And so if we set this up right, we're going to have, let's go with the sine of A over 12 equals the sine of 25 over 4. And so as I continue on, sine of angle A is 12 times the sine of 25 over 4. And so now I'm going to pull out my calculator, take the inverse sine, 12 times the sine of 25 degrees divided by 4. And I'm going to make sure that I'm in the right mode. I need to be in degree mode. And so when I hit, I get a domain error. And I think at that point, that's when you start realizing that you have an issue here and that there is no triangle formed. And so that would be our statement at this time. No triangle meets this condition. Now, if we make our circle just big enough, if we expand it until it just hits this third side in one spot, what we end up with is a right triangle formed. And we could take care of this in our right triangle trigonometry. Our radius of the circle is just going to be 12 times the sine of 25 degrees. Well, we don't need to deal with that here because, like I say, that's right triangle trig. We've dealt with that in other places. And the last case is our ambiguous case. Now ideally the ambiguous case takes place when the radius of the circle we're going to draw has to be less than the first side we drew. So it has to be less than 12. And it has to be just greater than the length that we get from our right triangle, which is 12 times the sine of 25. Now, I don't think at any point in our problem solving we're going to recognize that situation. What we're going to recognize is that the smaller of the two sides is opposite the given angle. And so our problem solving then determines, is it the situation where no triangle is formed or the ambiguous case is formed. So the first thing I'm going to do is deal with this triangle right here with that as part A. Alright, so side length is the radius of the circle of 7. And so when I go and set up my law of sines here, sine of A over 12, again, equals the sine of 25 over 7. And when I do this, I find angle A. And all of you are capable of doing this on your own. So I'm just going to punch this up myself. 12 sine 25 divided by 7. And then take the inverse sine of that. And so what I end up with here, let's just go to the nearest degree, 46 degrees. Alright, so if we have 46 degrees there, then we could do a little triangle sum theorem. 25 and 46, 71 degrees means this is 109 degrees. And so now we can go through our law of sines one more time and say, well, let's just call this side C. Now, we would go C over the sine of 109 degrees equals, now let's go back to the part that we knew and go with 7 over the sine of 25. I always try and avoid in my problem solving using sides that I found previously. And so that's why I went with sine of 25 and 7. I guess at this point I also could have used 46 degrees or the sine of 46 degrees and 12. You go through and solve this, you find that C ends up being, so we would have 7 sine 109 divided by the sine of 25, and I get 15.7 units. So now, since I have a triangle formed in this condition, that guarantees that there is a second triangle formed. And so what we have to do now is this goes back, and that's going to be still angle A, but since it's in a second triangle, let's, for the sake of this argument, call it A prime. So what's the measure of A prime going to be? Well, we could use the fact that this side right here is still 7. It's still the radius of the circle, and so the two radii form an isosceles triangle. So if this is 46, that's 46, and this angle A prime is going to be 180 minus 46, which is 134 degrees. And so now we didn't have to use the law of sines with that, just a little geometry knowledge. 25 and 34 is 159, and so this would be 21 degrees up here. And let's call this side right here C prime. And when we do that, find C prime with the law of sines. C prime over the sine of 21 equals, alright, let's see, let's go back with 7 times the sine of 25. And in this case, C prime is going to be 7 sine 21 divided by the sine of 25 gives me an answer of 5.9. And that certainly makes sense that it should be significantly less than C due to the nature of how the diagram sets up with the 3 different triangles. So hopefully that helps you recognize the ambiguous case. And just to reiterate, the number one thing we look for is the side-side-side condition and the fact that the smaller of the two sides is opposite the given angle.